So let us start. We are going to discuss now light entering a uniaxial crystal from air. So I have air here, for which I will assume the refractive index is 1 and light is entering at normal incident. That's the way I'm going to work. This I will call x3 equal to 0 is the surface. This is the crystal, and I have epsilon 3, and that will be the direction of optic axis. And light is entering from this direction. There will be a reflected beam and there will be a transmitted beam. Very similar to what we discussed for an isotropic medium. So I will have Ki incident, I will write incident, K reflected, K transmitted. All of them will be in the z direction, and that follows from the following constraint. One, this will come from the boundary condition. We know the time dependence that we are going to write is of the form e to the power of I k I minus omega I, ki dot r minus omega I t for the incident ray. This is the kind of argument we had used earlier, and e to the power of I kr dot r for reflected, this incident reflected, minus omega r t, and e to the power of I kt dot r minus omega t t. Since at the boundary condition must be satisfied for all times, we have omega I equal to omega r equal to omega t. And the relation between k follows from the velocity vector. Velocity in a medium is different from the velocity in air. So we have for that air, it is ki is equal to kr magnitude equal to omega by c. So immediately I get the law of reflection, theta I is equal to theta r. On the other hand, we also have for kt equal to n k n c by omega c by n. Omega. So omega c by n, therefore I will get kt equal to kt will be equal to this is correct, n by c. Kt is n k I or equal to n k r reflected incident transmitted. Okay. So those relations follow, except that n that we are talking about is in the direction inside the quasi crystal. Inside the not quasi crystal but uniaxial crystal. Okay, so having done that, this is the boundary condition for checking this. But there are boundary conditions on the electric field and the magnetic field, which we had already written earlier, coming from Maxwell's equations, and let me write them down again. D dot n, B dot n are continuous. E cross n, H cross n are continuous. except in our case H and B are just related by mu 0, so you might as well write B cross N to be continuous. This essentially implies B cross N is continuous. So these are at the boundary. These are for the boundary condition at x3 equal to 0. So now let's apply this and see what results we get. Since the optic axis is in this direction, we have the following situation. If K is along epsilon 3, my incident D incident is along epsilon 1, epsilon 2 plane, is in. But in that direction, for a uniaxial crystal, the refractive, as it enters here, the refractive index is the same. So what one would expect is that if it were polarized in that direction, it will continue to be polarized in that, which will just change from 1 to NO. So for all practical purposes, the result that we should get is that N refractive index will be replaced by NO, because any vector pointing perpendicular to epsilon 3 will have epsilon 1 equal to epsilon 2 as its dielectric constant after it enters the medium, which corresponds to ordinary refractive index. This can be verified, and this is a homework problem for you. I will write down the relevant equations which I want to check. Incident, I will write it as D incident epsilon 1, E incident you can write. These are the things which you will have to write. D is equal to dr reflected epsilon 1 plus, I do not know whether there will be something along epsilon 2 when it is reflected. D transmitted will be equal to D transmitted epsilon 1 plus D transmitted prime epsilon 2. Once I have written this, you can write down B and H. So B in this case would be DE incident. It will be K cross E incident by C. This is incident, and you can write that down explicitly. So I will write down one expression for B incident will be equal to K is along epsilon 3 and D is along epsilon 1. So epsilon 2 D, this will be K by C. Did I write correctly? Isn't it omega here? Yeah, this is omega. So K by omega times, what will I get? Epsilon 2 times E. Which is E in epsilon 2 by C. Similarly, you can write for the others using D here and here. And in this case, notice that you will be dividing by epsilon 1 here and epsilon 2 here to get the electric field. but epsilon 1 is equal to epsilon 2, nothing very much will change. If you match the boundary conditions as we did for the isotropic case, you will end up with the result dr prime equal to d reflected d transverse prime equal to 0. And you will find that only thing that will be transmitted will be this term and this term. This will be 0, this will be 0. This is straightforward work, almost identical to what was done for the isotropic case. So I will not discuss this any further. Now we will discuss the more interesting case when the optic axis is along the surface of the crystal. So I write down my direction. This is my epsilon 3 and my epsilon 2. I will denote the direction of optical axis by it will along here, optic axis, which normally I will call it eta 3. Earlier I used to call it epsilon 1, epsilon 2, epsilon 3. I have reserved epsilon 1 and epsilon 2 for epsilon 3 for the direction of motion of k, and my optic axis is going to keep changing in that direction. That's my epsilon 3. So here is my k I incident, k reflected, and k transmitted. Let's analyze this now. If the incident ray has a polarization, D has a polarization along epsilon, this is epsilon 1, is along epsilon 2, then the one which will enter here will be along epsilon 2. Again, you can derive that, and once you have it's along epsilon 2, then we know it will travel like an ordinary ray. So something which is moving with polarization like that will have velocity v0. On the other hand, if it were polarized along epsilon 1, and when it enters it will have epsilon 1, and then you can find out that it will be polarized along this direction, which corresponds to v optic axis is in the direction. So this has epsilon 3. Optic axis direction is epsilon 3. So the ray which will be moving like that will move with VE. So both the rays will come down, but one will have a larger velocity. In the way I have written for quartz, it will be VO will be larger and VV will be smaller. This analysis you can do writing D and D. Again, I will not repeat that algebra. It is quite straightforward, and it is something which can be done by matching boundary conditions. Physically, this should be clear.